We have left off in the exercise 2 sets. Your task is to divide the numbers 1, 2 until n into 2 sets of equal sum. The only input line contains an integer n. Print yes if the division is possible and no otherwise. After this, if the division is possible, print an example of how to create the sets. First, print the number of elements in the first set, followed by the elements themselves in a separate line, and then print the second set in a similar way. So, if we get as an input n 7, we have a range from 1, 2, 3 until 7, right? And maybe remember the formula to calculate the sum of this range would be n times n plus 1 divided by 2. Alright? So in this case this would be 7 times 8 divided by 2. This would be 28. Right? So if we have the sum of these, so when we have the sum of this main container, we can divide it by 2, and this would be 14, right? So we know, when we imagine here, we have the main container, 1, 2, 3, 4, 5, 6, 7. So the sum would be 28, right? And then we can divide this by 2, and then we know the two containers here have to have a sum of 14, right? And as you can see in the solution, it is possible. So in the first container we have 4 integers, 1, 2, 4 and 7. And in the second container we have 3 integers, 3, 5 and 6. And the sum of these integers and the sum of these integers is equal 14, right? Now, in case of 6, it's not possible, right? Because 6 times 7 divided by 2 would be 21, right? And we can't then split 21 by 2. It's not possible, so we print out no. But in case of 7, as you can see over here, it is possible. So let's go through this step by step. First of all, we take the integer n, right? Trim the input, we parse it like that. So we have the integer n. Then we want to create 2 containers, right? We have here the main container and we split it into 2 containers. So let's create them. I will call them A and B. So we have here created 2 vectors A and B. Now let's calculate the sum of the main container, right? We have said that this would be 28. So sum would be n times n plus 1 divided by 2, right? So in case we get as n 7, this would be 28, right? So now we have to check, can we divide this by 2, right? So if we can't divide it by 2, then we print out no, like in this example, and we terminate the program, right? So if the remainder of a division by 2 is not 0, then we know it's not possible to divide it by 2. Otherwise, in case of 7, we can divide 28 by 2, so we have 14. So let's divide sum by 2. That means sum is now 14, right? So this would be the sum of the integers in each container. And then what we can do is we have here the range 1, 2, 3, 4, 5, 6, 7, right? We want to put this in 2 containers. What we can do is we start at the last index and we put that in the first container, all right? Then we have put here 7, meaning we can subtract 7 from the sum of the container, so 7 remains. Then we check the next element. Now I, in this case, is smaller or equal than 7, so we can put it here, right? And we subtract 6, then 1 remains. Now the next element is bigger than the remaining sum, so we put it in the second container. 4 is also bigger, 3 is bigger, and 2 is bigger. Now the last element, we have said that it should be smaller than or equal to the remaining sum, so 1 is equal to 1, so we put it here. So we put it here, and as you can see, 7 plus 6 plus 1 is 14. 5 plus 4 plus 3 plus 2 is 14. So we have splitted this range into 2 equal containers. So we iterate in a range from 1 to n, where n is included, and we start at the last element. So we call the reverse method, all right? And then in each iteration we check, is I smaller than or equal to the sum? If that is the case, then we subtract I from the sum and we push it into the first vector, all right? Otherwise, we push I to the second vector. The logic I've shown you right before. And then all we need to do is we have to output it in this format. So first of all we print yes. And then on the next line we print out the length of the first vector. Like that. Then in the next line we print all the elements from the first vector A. So we iterate, and for each element we print out the element, right? Then we print out the length of the second vector. And then we do the same. We iterate over all the elements in vector B and print it out. And in the end, to avoid a end of line symbol in the terminal, we print out an empty new line, right? Let's see. So I put in 7, and as you can see, this would be the correct output. And let's put 6. And we get back no. All right, let's submit this. 2 sets. And as you can see, all the tests have passed. All right, see you in the next one. Bit strings. Your task is to calculate the number of bit strings of length n. For example, if n equals 3, the correct answer is 8, because the possible bit strings are 000, 001, and so on. The only input line has an integer n. Print the result modulo 10 to the power of 9 plus 7. So as you can see, when we get an input of 3, meaning n is 3, then we output 8, because there are 8 possible bit strings with a length of 3, right? Let's consider if n is equal to 2, right? So we would have 00, 01, 0 1, 1 0 and 1 1. So we would have 4 possible combinations. And as you might notice, because we are here dealing with binary, we go with a base of 2. And to find the combinations, we just calculate 2 to the power of n, right? So for n equals 3, this would be 2 to the power of 3 would be 8, right? And 2 to the power of 2 would be 4. But of course, this would be too easy, right? So if we go in here and let's say n is equal to 3, and let's say 2u64 to the power of n. Now this would actually be working, but as you can notice, n can be any number between 1 and 10 to the power of 6. So 10 to the power of 6 would be 1 million, right? So if we had here 1 million, as you can see, we have an overflow, so it's not possible to solve it like that. But what we actually can do, now let's take for example 2 to the power of 3. Now 2 to the power of 3 would be 2 times 2 times 2, right? So when we start at 2 to the power of 0, which is 1, right? We multiply this by 2, we will get 2. Then we take the result and multiply it by 2 again, right? So we would have 4. And then again 2 times 4, and this would be 8. So we do this 3 times. Now, as you can see, we have to print the result modulo 10 to the power of 9 plus 7. Now, if we consider 2 to the power of 3 and we do modulo 10 to the power of 9 plus 7, this would be the same as doing it 2 times 1 modulo 10 to the power of 9 plus 7 times 2 times 2 modulo 10 to the power of 9 plus 7 times 2 times 3, 4, excuse me, modulo 10 to the power of 9 plus 7. This is exactly the same like this because of this rule in modulo arithmetic, right? So x to the power of 2 modulo c would be the same as x modulo c times x modulo c, and this times modulo c in the end. Alright? So the first thing is, let's do n3, and I want to create a constant, right? So we don't have to repeat that. And we have seen, let's write this 10 to the power of 9 plus 7, and this would be the number, right? So I try to paste this here, right? And like that. So we have a constant with the modulo, right? And we already calculated that, so the program doesn't have to calculate it once again. And then what we are doing basically is we go from 0 to n. So we are iterating. For example, if n is 3, then we iterate 3 times, right? Then we can fold. We start at 1. We take the accumulator, let's call it res, and we don't need the item in each iteration, so we leave it like that. And then what we can do is just in every iteration we multiply by 2 the accumulator, and we apply this modulo operator with the mod constant, right? And let's put this in a variable, and then we can print it out like this. So let's see if this is working. 8, and now let's put a bigger number. As you can see, this is working. So let's take actual input So like always, we take input, we trim it, parse it, and then store it in n. 3 would be 8. Let's go with 2, 4. This is correct. So let's submit that. And as you can see, this got accepted, and we can go as big as 1 million, right? So bit strings with length of 1 million. Alright, see you in the next one. Trailing zeros. Your task is to calculate the number of trailing zeros in the factorial n. For example, factorial 20 would be this number. So we have 4 trailing zeros, right? And factorial, let's say factorial 3 would be 3 times 2 times 1, right? Would be 6. In this case, we don't have a trailing zero. And one approach of solving this is if we have, for example, n20, right? So let's take this input 20, and the factorial we can then calculate the factorial by iterating from a range from 1 to n included, and then we just take the product, right? So we have the factorial. And let me print that out. Let's do U128. As you can see, this would be the result of 20 factorial, right? We have here 4 trailing zeros. So how can we find out how many trailing zeros there are? Basically, we take a counter, right? Let's set this to 0. And now we can check while factorial is divisible by 10. Then we increment count by 1, right? And then we divide factorial by 10. Then all we do is we print out the counter. Now, as you can see over here, we have 4 trailing zeros, so this is correct, right? But to be honest, this approach is not so efficient, right? We can actually find out how many trailing zeros there are without calculating the actual factorial or the result of the factorial. So how can we do that? Let's first take, for example, 5 factorial. 1 times 2 times 3 times 4 times 5. Now, to find out if this is divisible by 10, let's actually put here 5. And let's also print out the factorial. Right, the factorial would be 120. So we have 1 trailing zero over here, right? And to find out if this is divisible by 10 and how many times, we can take the number 10 and apply prime factorization. So 10 would be 2 times 5, right? These two are prime numbers. So what we then have to find out is in the factorialization how many pairs of 2 and 5s are there, right? So in this case we have 1 pair, meaning 5 factorial has 1 trailing 0. Now we have also to consider if we have 1 times 2 times 3 times 4. Now 4 in prime numbers would be 2 times 2, right? Times 5. Times 6, times 7, times 8, times 9, times 10, like that. As you can see, 10 would also be 2 times 5, right? So we would have 2 pairs, right? And if we go on, and we have, for example, 25. So 25 would be 5 times 5, right? So we have to consider this case. Now, because 2 is more common than 5, so in each range or in each operation like that, you will find more 2s than 5s. We will concentrate only on the 5s, right? So when we look for 2 5 pairs, we only look how many 5s there are, and we know there will be enough 2s to fill out, right? So what we then can do is, first of all, let's keep that as it is, and I will delete that because we won't have to actually calculate the factorialization. So let's call this res, and what we can do is, while n is bigger than 0, we divide by 5, so we check how many times can we divide n by 5, right? And we store this in the result variable. And then we actually divide n by 5, right? So in this case, we have here n, right, the input, and we check how many times can we divide n by 5, and we store that in res, and in each iteration we are dividing n by 5, right? So when we run that, as you can see, we get 1. So factorial 5 would be 120, and we have 1 trailing 0, so 5. So 5 can be divided by 5 one time, right? So we store that in res, and then we divide n by 5, so n would be 1, right? So in the next iteration, it's not possible to divide by 5 any further, right? So n will be 0, and then we terminate the loop and we print out the result. And let's take actual input here. Like that. Let's make this U64. Then we have the res and our for loop, right? So if we now put 20, we get 4 trailing zeros. Let's put 5, we get 1 trailing 0. So let's actually submit that. And as you can see, this got accepted. So for example, in a factorialization of this number, we get that many trailing zeros. See you in the next one. Coin piles. You have 2 coin piles containing A and B coins. On each move you can either remove 1 coin from the left pile and 2 coins from the right pile, or 2 coins from the left pile and 1 coin from the right pile. Your task is to efficiently find out if you can empty both the piles. The first input line has an integer t, the number of tests. After this there are t lines, each of which has 2 integers a and b, the numbers of coins in the piles. For each test, print yes if you can empty the piles and no otherwise. So, the first input line will be the number of tests. Now, we have pile A and pile B, right? So in pile A we have 2 coins, and in pile B we have 1 coin. And as you can see, on each move you can either remove 1 coin from left pile and 2 coins from right pile, or 2 coins from the left pile and 1 coin from the right pile. So what we can do is we remove 2 from this and 1 from this, so we have 1 move, right? And we print out yes, because we could empty both of the piles without leaving a rest, right? Let's consider the second one. A and B, we have 2 and we have 2, right? 2, 2. Now let's remove 2 from here and 1 from here. So we have one move, but as you can see, we have a rest. We have another coin over here. So we print out, no, it's not possible to empty both of the piles. Let's see 3, 3. So let's say we remove 2 from A and 1 from B. We have one move, and then we remove 2 from B and 1 from A. So we needed 2 moves, and as you can see, there is no rest, so we print out yes. So first of all, we have to consider, again, we can remove either 2 coins from A, and from B we can remove 1 coin, or we can remove 1 coin from A and 2 coins from B, right? So in each move we remove 3 coins in total, right? So from A and B we remove here 2 and here 1, so 3 coins. Or if we had 2 in B and 1 in A, it's the same thing, right? So in each move we remove 3 coins, and that means that the total amount of coins in the piles has to be divisible by 3, right? Otherwise it's not possible to empty both of the piles. The second thing we have to check, right, is if we have here 1 and here we have, let's say we have 2 here and 4 here, right? So this would be 6, and 6 is divisible by 3, right? So that's good. We can remove 2 from here, 1 from here, 2 from here, and 1 from here. So we had 2 moves, right? Now when we have here 2 and over here we have, let's say, here we have 6 and here we have 3, right? We have 9. 9 is divisible by 3. And when we remove here 2 and here 1, here 2 and here 1, right, it's also possible. But there is a case where it's not possible. If we have here 5 coins, right, and here 1, we have 6, and this is divisible by 3, right? So we have 2. But the problem here is we have a rest, so this would not be possible. So as you can notice, we are removing either 2 from A and 1 from B, or 1 from A and 2 from B. So the ratio we remove coins is 2 to 1. That means that the larger pile shouldn't have more coins than 2 times A, right? So over here we have 5 and over here we have 1. So 2 times 1 would be 2, right? So this is larger than 2 times A, right? So the bigger pile should not be more than 2 times bigger than the smaller pile. Alright, so so let's first take input, and we will store that in a vector of a tuple of U64, U64, right? So in each line we will parse these numbers and put it in U64 tuples, right? And we do that for each line, and then in the end we will store all of the lines in a vector. So we have a vector of tuples of U64, U64. So we skip the first line. We do flat map, and we split on white space, right? So then we will get a tuple A and B, and we parse both of them, right? and then we collect it like that. Then we collect it like that. So in input we have now a vector of U64 tuples, right? So let's iterate over the input. So for each line in input or for each element in the vector, we get back a tuple A and B. So let's check if A plus B is not divisible by 3, right? So the modulo operator will not return 0 when we divide by 3. Then we print out no, right? There is no possible solution. The second case we have seen is if A is bigger than 2 times B, or B is bigger than 2 times A, then it's also not possible, right? So because we are removing coins in a 2:1 ratio, the bigger pile should not be more than 2 times bigger than the smaller pile, and we check it like that. So if any of these cases evaluates to true, then we print out false or no. Otherwise, we print out yes. So let's check this. 3, 2, 1, 2, 2, 3, 3. As you can see, yes, no, and yes. This is the correct output. Alright, let's submit coin piles. And this got accepted. As you can see, we have here very large tests, right? So we do this with a lot of numbers, and this got accepted. See you in the next one. Palindrome Reorder. Given a string, your task is to reorder its letters in such a way that it becomes a palindrome, i.e. it reads the same forwards and backwards. The only input line has a string of length n consisting of characters A to Z. Print a palindrome consisting of the characters of the original string. You may print any valid solution. If there are no solutions, print no solution. So a palindrome is when we have, for example, AA, BB, we reorder the letter so it becomes A, B, B, A, right? It reads the same forwards and backwards, right? And the best way to solve this is when we have AA, BB, we store this in a hash map. So this hash map will have A is 2 times and B is 2 times, right? And when we have an input string where the character counts are even, we can for sure create a palindrome, right? So D, D, C, C, all of them have count 2, right? They appear 2 times, or you could even have 4, right? This is also even. And we can create a palindrome from that without problem. We can take A, B, D, C, 4 times A, 4 times E, then C, D, B, A, right? And notice something, a palindrome basically is like a mirror, right? So we have A, B, B. What we do is we have a character count 2 and 2. We take 1 from this, 1 from this, and then we mirror, right? So we take B and A. So all we have to do then is take this and reverse it, right? Now what about uneven counts? So if we had A, B, B, and C, right? So if one character count, if we have A2, B2, and C1, as you can see, the character count for C is uneven. What we do with uneven characters, we put it in the middle. So we take A, B, C, B, A, right? So this is in the middle, and this is a perfect palindrome. This is also possible A, B, B, 3 times C. Again, we do the same thing. We take A, B, 3 times C. This we put in the middle, and then B, A. We mirror this over here, right? The problem is if we have D here, for example, which is also uneven, right? We have C3 and D1. Then it's never possible to create a palindrome. So we print out no solution. So we have to ensure that the character count for uneven characters is never bigger than 1. We can only have a character which appears in the string unevenly once, right? So for example, 3 times C is no problem. If this D is not here, then we have only one type of character which is uneven, right? Then we just put it in the middle. That's basically all that is to it. So let's try. And the first thing I want to do is I want to import standard collections hash map. So as you can see, we are importing that, and then over here we take input, we do string, so we have input, and then let's create the map. So we take the input, we trim it, and we iterate over the characters, right? So when we get an input string, we iterate over each character. And then we can use fold over here. And we want to fold this into a hash map, right? So we call the accumulator map and the character in each iteration. Character is C, right? So then in the map we check, is there already an entry for the character we are iterating over, right? So we pass this here, is there an entry for the character? If there isn't, then we insert it with a count of 1, right? If there is already a character, right? We take the count and we increment it by 1, right? Like that. And in the end, we return the map. So we have now here the map. So let me print that out so you can see what this looks like. So if we now pass to this a string, AABB, as you can see, we get the characters and its counts. For example, we have 2A and 2B. Let's go with A, B, B, C, 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 D, 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 right? So B2, A2, C4, and D3, right? So what we now have to check in the hash map, are there more than one character with uneven counts, right? So we map over the values, right? So let's say we have A2, B1, and C3, right? We iterate over these values and we filter for elements, right, in the values that are not divisible by 2, right? We do it like that. And then we want the count. So if the count is bigger, right, in this case, these two are uneven. So we have 2 over here. That means it's not possible to create a palindrome, right? So we just print out no solution. Like that. And then we just terminate, right? So let's say we have A and 3 times B. So we have character count. B, which is 3, and A, which is 1. So both are uneven, meaning there can't be a solution, right? And then let me create 2 strings, even and odd, right? Like that. So in the even string, we will push the characters with even counts, for example A, and let's remove that. And in the odd string, we will push characters with uneven counts, right? So we now iterate over the map, and if the count is not divisible by 2, right, then we push it to odd. Push stir, and we have to push it count times, right? So if we have C and the count is 3, we have here the odd string, right, which is empty right now. So now we have to push it to this 3 times, so C, 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 right? Otherwise, if the count is even, then we will push to even, but we will push over here, we will push it count divided by 2 times, right? So if we have A2 and B2, then we push to the even string, A 1 time and B 1 time, right? The count is 2 and we divide it by 2, so we push 1 time A, and B is also 2 divided by 2, meaning we push B, right, 1 time. And I will show you why we are doing that. If we now print out even and odd, right? If we have A, A, B, B, C, 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 right? As you can see, we have 2 times A, 2 times B, and 3 times C. So we push to the even one the characters with even counts, right? So we push B and we push A, and to the odd one we push 3 times C. Now, why are we doing that? Because now we have BA, CCC, and all we have to do now is just reversing this, right? So we take A, B, and then we have a palindrome, right? So we have here 3 elements. We print even, we print odd, and then even chars we reverse. So we are iterating over the chars in the even string. We reverse it, and then we collect it into a string, right? And that's it. Let's see. Let's go with this. As you can see, C, A, B, A, C. So this is a palindrome, right? And it doesn't matter actually the order, because all that matters is that it's a palindrome, right? So I have to remove this print line over here, like that. And yeah, let's try to submit that. As you can see, this got accepted. Alright, see you in the next one. Gray code. A gray code is a list of all 2 to the power of n bit strings of length n, where any 2 successive strings differ in exactly 1 bit, i.e. their hammering distance is 1. Your task is to create a gray code for a given length n. The only input line has an integer n. Print 2 to the power of n lines that describe the gray code. You can print any valid solution. So, as you can see here, when we get input 2, we will print out 4 numbers of gray code. Basically 2 to the power of 2 possibilities, right? 4. Now, if we do this in binary, right, we would have 0, 0, 0, 1, 1, 0, and 1, 1. So this is 0, 1, 2, 3 in binary. Now in gray code, we would have 0 0, 0 1, 1 1 and 1 0, right? So the difference between binary and gray code is that the distance of the numbers in gray code is always 1 bit, right? So we have here 0 0, then we change only 1 bit, 0 1, then again we change only this bit here, 1 1, and then we change this bit, 1 0. Whereas in binary, as you can see, we have 0 0, 0 1, and over here we are changing 1 to 0 and 0 to 1, so we have a distance of 2. And in gray code, no matter the sequence, the distance is always 1. So all we basically have to do here is convert the binary to gray code, right? So how do we convert a binary number to gray code? So let's take, for example, 1 0 in binary, right? So what we do is we take the most significant bit, like that, and then we XOR this over here. So 1 0 would be the output, XOR 1 0 would be 1, right? So in XOR, if we create here a truth table, when we have input 1 0, we output 1. If we have 0 1, we output 1. If we have 1 1, we output 0, and 0 0, we output 0, right? So XOR only outputs 1 if the inputs are different, right? If they are the same, we will return 0. And that's basically it, right? So 1 0 in binary would be 1 1 in gray code, and we have seen that over here. If we have this in binary, the next binary number would be 1 0, but in gray code it's 1 1. Alright, so we take the input, standard IO read to string, standard IO standard int, unwrap, trim, parse, and unwrap, like that. Use 64, and then because we have to print out 2 to the power of n lines, right? So we go from 0 to 2 to the power of n, right? Like that. And then for each binary number, right? So in the first iteration it would be 0 0, right? In the second one 0 1, and so on. So what we are doing is we want now to convert in each iteration the binary number to gray code. Gray code. Alright? And we have seen that we take the binary number and we take the most significant bit and then XOR these two bits, and we have gray code, right? So how would we do that in the program? If we, for example, have the binary number 1011, right? Now we want to XOR every bit except the first one. So what we can do is we right shift by 1, right? So when we right shift this over here by 1, then we would have 0 1 0 1, right? And then what we are doing is we XOR. So that means 1 0 will be 1, right? 1 0 will be 1, 0 1 would be 1, 1 0 would be 1, and 1 1 would be 0. So we have converted this binary number to gray code, right? And what we are doing then is in each iteration we take the binary number and we XOR the binary number by the binary number right shifted by 1, right? So we right shift by 1 bit, right? This is the notion for a bit. And that's basically it. So let's call this over here n. So now if I run that, if I put 2, we would have 0, 1, 3, 2. Now of course we have to output this in binary. We have now outputted it as decimal, right? So we can output by providing here b, right? If I run that again, I put 2, as you can see, we get 0, we get 1, we get 1, 1, and we get 1, 10, right? Now, what we need to do actually is we have to provide the proper padding, right? We have here a length of 2, so the binary number here should be 0, 0, length of 2. Here it should be 0, 1. So we will do that padding with zeros, and let's say 2 positions. All right. Two positions, and as you can see, we now have the proper padding. But now this isn't working when we have as input 3, right? So if we have 3, as you can see, these are not aligned correctly. So what we have to do is we have to pad here by the number n, right? So we can do that by putting here $1 sign, and then we can provide here a second argument, and this should be the proper padding, right? So, and as you can see, n should be of type U size. So let's change that like that. And we have to convert this here to U32 because the POW method takes as argument U32. If I do that again, let's say 2 working, let's say 3, and you can see the gray codes are now properly aligned. So to make this a little bit more concise, we can actually over here left shift by n. Alright, we can here left shift 1 bit by n. Like that. And we can do that because when we start with 1 and we left shift, right? So let's take, for example, 2 to the power of 2, right? The input n over here would be 2. Then we left shift by 2, right? So we have then 0, 1, 0, 0, and this would be binary 4, right? This would be the correct result. And 2 to the power of 3, we would left shift 3, so we would have 1, 0, 0, 0, right? So we left shift this by 3, we left shift this over here by 3, and we will get 8. So this is the binary number 8 in decimal. Alright, so we can do it like that, and that's basically it. Let's check again, 2, 3, and as you can see, in every iteration we are only ever changing one single bit, right? Let's submit that. Gray code. And this got accepted. See you in the next one. Tower of Hanoi. The Tower of Hanoi game consists of 3 stacks, left, middle and right, and n round discs of different sizes. Initially, the left stack has all the discs in increasing order of size from top to bottom. The goal is to move all the discs to the right stack using the middle stack. On each move you can move the uppermost disc from a stack to another stack. In addition, it is not allowed to place a larger disc on a smaller disc. Your task is to find a solution that minimizes the number of moves. The only input line has an integer n, the number of disks. First print an integer k, the minimum number of moves. After this, print k lines that describes the moves. Each line has two integers a and b. You move a disk from stack A to stack B, right? So I want to show you the Tower of Hanoi game, and that's it, right? So the rules are pretty simple. We have to put all of these disks in the same order to this, right? We can in each move take only one disk, the uppermost one, and we can't place a larger disk on a smaller disk, right? So when we have 3 disks, the minimum moves are 7. So what we are doing, we first take this one over here, then we place this over here, this over there, then we can take this one, we put that back, we can place this one here and this one here. As you can see, I've done it in 7 moves. Let's see with 4 disks. So we put this over here, we put this over here, like this. Then we can put these back here, and now we can move the biggest one to the last pile. Now we remove that, we put it back to the source, and then we can move them like that. As you can see, 15 moves. Now our task is to find the minimum moves and how do we move these disks. I want actually to take here only 2 disks, but it's not possible. So just imagine this disk over here. Just imagine this disk over here isn't there, right? So what are we doing? First of all, we take this uppermost disk and put it in the middle, right? Then we take this and put it to the target, and then we put this, right? And with 2 disks, this would be finished. Now with 3 disks, it's basically the same thing. We take this over there and we put this over here, right? Now, the last step is always to put this over here to the last pile. And as you can see, what we have done is we have taken n-1 disks, so all the disks except the largest one, and put it in the temporary pile. Then the last step is to put this over here, and then we just move the disks in the temporary pile. We use this now as temporary, and we move these over there, right? Like this. With 4 disks, exactly the same thing. So we move n-1 disks to the middle pile, right? So n-1 would be 3, and then we take the nth disks, and then we take the last disk and we put it over there. And then all we need to do, we can take these and we put it over here, right? So we move them from this to this, using the source as temporary. So this really is a classical example of recursive programming. Let's first take the input. Like that. Let's give here U8. This doesn't need to be so big. And first thing we need to do is we have to decide, or we have to output the minimum number of moves. So for 2 disks, the output would be 3, right? 3 moves. So when we have 2 disks over here, we take this one here and this one here, then this over here, we take this, like that. So we have 3 moves, from 1 to 2, we take the larger disk from 1 to 3, and then the smaller disk from 2 we put to 3, right? And it's all the same basically. It's always the same tactics. So when we have here 3 disks, right? We put this here, we put this here, and then we put this there. So we have here 2 disks, and then the largest one we put over there, right? And then we basically, if this is source, this is temp, this is target, then we use this as temporary, and we move these two, one here, then the larger one here, and then we move it back. It's always the same, and that's why we can use recursive programming. So the number of moves is 2 to the power of 2 minus 1, right? So 2 to the power of 2 would be 4, minus 1 is 3, right? If we had 3 disks, it would be 2 to the power of 3 minus 1, right? 8 minus 1 is 7. So we can print that out. And let's use left shifting, because we have seen that in the exercise before. So we take one bit, we left shift it by n, and then minus 1, right? So if I now run this, 2 disks, 3, right? Minimum move 3 would be 7. Let's see, 4 disks would be 15. 15. So this is correct. And then what we can do is we can create here a function, and we pass some integers. Like that. All right. Now we call this function over here. Let's call it Hanoi. And over here we pass the number of disks, right? So n would be the number of disks, right? Then source will be 1, temp will be 2, and target will be 3, right? Because as you can see, we are here having these numbers. So we move from pile 1 to pile 2, then from pile 1 to pile 3, and so on. So if we had 3 piles, let's call this source, temp, target, and this would be, because we have to output numbers, 1, 2, 3, right? Source, temp, and target. Then we have to define our base case. So if n is equal to 0, we just return, right? So that's the case when no disk is left, right? If we have 0 disks, then we just return. And then we can use recursion. So we have seen that for n minus 1 disks, we put them from source to temp, right? We put them from source from 1 to 2. All right. So when we call the Hanoi function over here, we pass as temporary 3, and we pass as target 2, right? Because we want n minus 1 disks to be in this, so we can then move the biggest one over there, right? And in each move, and every time we do that, we want to print source and target, right? Every time we do that, every time we move this, then we print out source and target, right? From 1 to 2, from 1 to 3, and so on. And notice again, when we move this disk over here from this to there, then temporary will be the target, because we are passing here temp, which is 2, to target, right? And then all we need to do is the ones left over here, we again call n minus 1, and we put them from temp, right? So we pass temp as source here, and we move them to target, to 3. All right, that's basically all we are doing. Let's see, 3, and these would be the steps, Now let's see if this is correct when we put in 2. So we get 3 steps, right? And we move from 1 to 2, then from 1 to 3, and from 2 to 3. So this is correct. And just to see what is happening, let's actually simulate over here a called stack. So we are calling the Hanoi function, right? With number of disks, let's say 2, right? And then we pass 1, 2, 3. So 1 for source, 2 for temporary, and 3 for target, right? Then we check, is n equal to 0? No, it's 2, right? So then we call recursively Hanoi n minus 1. So 2 minus 1 would be 1. Then we pass source. And as you can see, we then pass target. So target is 3 and temp is 2, right? And then this function gets called. So we enter again, is n equal to 0? No, it's 1. So then we again call the Hanoi function. This time this is 0, 1, and then we take, as you can see, we called the function like that. That means when we now take target is 2, right? So we take target and we take the other one, the temporary one. Then we call this function. Now we call this function and we check, is n equal to 0? Yes, right? That means we return. So in this case, the call stack will collapse, right? So we return, meaning we go back and then we go back to this, right? So we have left off over here, and then we are printing out source and target. So 1, 2, right? 1 and 2. And then, as you can see, we call the Hanoi function again. n minus 1 would be 0, right? And then temp. So temp in this case would be 3, right? And temp would be 3 and source would be 1 and target would be 2, right? So we call this, and as you can see, n is 0, so we return, right? So we have done that, and then we go over here. So we have left off here, and then we print out source and target 1, 3, right? And then we call Hanoi again. So we call, let's put another color, Hanoi, n minus 1 would be 1, and we call it with temp, right? 2, source is 1, and target is 3, right? So we execute this function. We go here, n is not equal to 0. So we call this over here, h, n minus 1 would be 0, source would be 2, and target would be 3, and temp would be 1, right? And then we call this function, and as you can see, n is equal to 1, so this gets collapsed, we return, and then this over here, we print out source and target, right? 2 and 3, and that's basically it, right? We have executed all the functions in the call stack. So this will be the output: 1, 2, 1, 3, and 2, 3. Let's see if this is accepted. And as you can see, this got accepted. And as you can see, we do that with real high numbers of disks. For example, 15, right? We would have 32,767 possible steps we have to undertake. Alright, see you in the next one.